Greetings and welcome to Vector Addition Graphical Method. In this video, we're going to learn how to add two vector quantities, two or more actually, vector quantities, when they're in more than one dimension, in particular 2 dimensions. And so this is going to be a little different than what we had to do in the last unit where we were always stuck in one-dimensional motion. So here's our example. You walk 75 meters west and then 50 meters south. What is your displacement? Now we're going to employ what's called the graphical method of vector addition. In other words, we're going to draw a diagram to represent this motion, and then we're going to draw it with a ruler and a protractor. Okay? Now eventually we will use trigonometry, right triangle trig only, in order to find our answers. And certainly as we go through and draw our diagram, some of you are going to imagine the right triangle trig we might use. But we're going to hold off on that right now because we have to draw a good diagram even when we're using the trig. Otherwise, it's hard to imagine what trig to use. So, I want to draw vectors to represent walking 75 meters west and 50 meters south. As we talked about yesterday, we are going to use arrows to represent these individual displacements because arrows have a size and they have a direction. Now, in order to draw this arrow, we need to be able to draw it so that it fits the screen. I mean, we can't draw an arrow that's 75 meters long. So we're going to use, just like you would on any map, a scale. Now the scale I'm choosing is 1 centimeter, or 1.0 centimeters of drawing, is equal to 5.0 meters in real life. Usually when you pick a scale, you try to pick numbers that are fairly easy to use. You wouldn't want to use a whole bunch of decimal places or fractions because then that gets really difficult to convert. Right? So I'm choosing a nice 1 to 5 scale here. So if I wanted to draw a 75 meter west displacement, how long would my arrow have to be? Well, since it's 1 to 5, hopefully you can figure out that it should be 15 centimeters long. And since it's pointing west, using our normal cardinal directions, that would be to the left. So here's where I'm going to draw the arrow from. I'm going to lay down my ruler. Okay, this ruler happens to be calibrated in centimeters. And I'm going to draw a 15 centimeter long arrow. Notice here the head of the arrow is part of the drawing. Right? The head is part of the arrow. So you have to go from the tip to the tail here for the 15 centimeters. And I've labeled it 75 meters. So our next question is, what would a 50 meters south displacement look like? Well, if this drawing is going to make any sense at all, we have to use the same scale. So 50 meters in the real world, since we're using a 1 to 5 scale, would be 10 centimeters in my drawing. And since I'm drawing south, south is of course down. So I'm going to draw a 10 centimeter arrow pointing down. But where do you think I should draw it from? Well, since we walked west and then we're going to walk south, we might as well put it right here, right? That's where we ended up after walking 75 meters west. So I'm going to put a new set of crosshairs there. And I'm going to put my ruler pointing straight down and draw a 10 centimeter long arrow to represent 50 meters south. Now, one little thing here, if you're actually drawing this, like on the worksheet you'll do after this video, you're going to have to make sure that this angle in here is 90. I would actually use a protractor. Don't just eyeball it. Because if you just eyeball it and you're off by a few degrees, you're throwing error into your drawing. Okay, I'm, of course, drawing to a perfect scale with perfect angles because I'm drawing this using PowerPoint, but you're going to want to put a protractor there and make sure it's 90 degrees. So our next question is going to be, how could we represent the displacement over the entire trip? Well, first of all, remember what displacement means. It's your change in position, how much out of place you are. And so if we started here, walked 75 west and then 50 meters south, and we ended up here, our displacement could be an arrow there. An arrow starting where we started walking and ending where we finished. And notice again that the head of the arrow is part of the arrow, right here. And once we draw this in, all we need to do then is use our scale and a ruler to figure out what that displacement actually is in the real world. If you count off here, this looks to be about exactly 18. And since this is calibrated to the nearest centimeter, we can estimate to the nearest tenth of a centimeter, which would make it about 18.0 centimeters. Using our 1 to 5 conversion, that would be 90.0 meters in real life. Now that's not enough because remember, displacement is a vector quantity. Last unit, all we needed was right or left, up or down, positive or negative. But here we're in 2 dimensions. So to describe this displacement in 2 dimensions, we need more than just how long the displacement is. We also need an angle. And you always look at the tail of a vector to find its direction. So we're going to slap a protractor on there. If you remember my protractor, each one of these lines is 10 degrees. And since it's calibrated to the nearest 10, we can estimate to the nearest degree. So this to me looks to be about 10, 20, 30, and maybe a little less than halfway. So I'm going to say about 34 degrees. Now again, this vector is a displacement, and I'm going to use a symbol for that. The symbol I'm going to use is D, right, with an arrow. Don't ask why they're putting this little space over here. I don't know. Now, D stands for displacement, and it needs an arrow because displacement is a vector quantity. Last unit we used delta x for displacement, but that's because we were in only 1 dimension. So it meant change in horizontal position. Since this is 2-dimensional, it's traditional to use a D with an arrow. Now we have to name this vector. Well, the length isn't too hard. The displacement is 90.0 meters at 34 degrees. This is where the weird part's going to come in, but again, think about the naming we did on the last worksheet. South of west. Right? Here's the west, and we have to rotate to the south. So 90.0 meters at 34 degrees south of west is your displacement. Now realize what this displacement tells you. You could walk 75 meters west, 50 meters south, and end up right there. Or you could walk 90.0 meters at 34 degrees south of west and end up in exactly the same place. So notice that this displacement vector replaces the sum of these 2 vectors. And so it's called, in vector algebra language, a resultant. You might call it a resultant displacement. This is the one vector whose effect on a body is the same as the net effect of 2 or more other vectors. And we're going to talk about adding more than 2 in a moment here. So in other words, again, 90 meters at 34 degrees south of west will get you here. And it replaces going 75 west and 50 south. So it's kind of a handy thing. It's the net effect of all those vectors. It is what is known as a resultant. Now, to find a resultant using the graphical method, we drew one vector to a scale. Now, technically, it doesn't matter which one you draw first, but there is a rule of thumb. Remember, a rule of thumb is not something that you have to do, but it's just a convention that people generally agree to. In general, you will see me draw the horizontal vector first. Do I have to? No. And if you don't, you're not going to get it wrong. You might have a different angle, a slightly different name, but you'll still get full credit. The second thing we did, okay, so there we drew the first vector. Second thing we did, we drew the vector to the same scale. But we didn't just put it anywhere. We placed the tail of the second at the head of the first. This is really important because this is a general thing. Head-to-tail construction is vector addition. This is how you add 2-dimensional vectors. I mean, you could do it with 1-dimensional. You went 75 west, and then you go another 50 west. You'd end up 125 west from where you started. But in 2 dimensions, it's really important to draw them head to tail. And then the last one, we drew the resultant vector. And we didn't just draw it anywhere. We drew it from the tail of the first vector to the head of the last. Now, why did I use this first to last instead of second? Because you could actually do this process with 200 vectors. You just have to repeat step 2. In other words, just keep drawing the vectors head to tail, head to tail, head to tail, head to tail. And when you get all done with all your vectors, and they may cross each other and overlap and do all sorts of weird things, if you draw a vector from the tail of the first to the head of the last, that is your net effect. That is your resultant. And this process is actually even more general than we're making it out. I did displacements in my example because I think they're a little easier to understand what we're doing. But you could add 2 velocities this way. You could add other things that we're going to talk about this year, like forces or momentums or anything really that's a vector can be added by drawing the vectors head to tail. So I hope you've enjoyed this, and on your next worksheet, you're going to be doing some of this yourself.